Okay, here I'm just going to do a couple of example problems that should help you with the assigned problems. So in the first one, let's say that we have a disk that's connected to the wall by a pin. This is sort of like a pizza cutter looking thing. So this arm is connected to the center of the disk and connected to the wall. And at this instant, the disk has an angular velocity of 10 radians per second, positive, so that's counterclockwise. And we'll say that this point here has a force applied to it of 20 newtons. This disk will say has a radius of 0.3 meters and a mass of 0.5 kilograms. And let's calculate what the acceleration is of this point on the disk. So I'll call this A, and we want to calculate the acceleration vector of that point A. Okay, so the hinge is going to be the center. And we're going to use rotational Newton's second law to calculate the angular acceleration. And then from that point on, it's just like the rotational kinematics problems you did. It's very much like circular motion. So I'm going to start with a free body diagram. And there are a few things going on at the middle. There's the weight of the disk. That always acts at the center of the object. So that's 0.5 times 9.8. So that's 4.9. And then there are the unknown forces that are applied by the hinge. I'll call those Rx and Ry. And then there's the force down here at the bottom of 20 newtons. And those are all the forces acting. The moment of inertia, we're doing this calculation about the center because that's where the hinge is. So this is going to be 1/2 times the mass times the radius squared. And that gives 0.0225 kilogram meters squared. So that's the moment of inertia. And now we have to calculate the moments produced by all these forces. There's 3 forces here. The moment produced, or the torque produced, by these forces Rx and Ry, well, both of them act at the hinge, and so the distance is 0, and so the moment has to be 0. The weight force, this one often produces a moment, but since in this case it's acting, the line of action of this weight force goes right through where the hinge is. D is 0 for this too. That distance is 0, so the moment is 0. And then the last one we have is this 20 Newton force. That's plus or minus. That force is already perpendicular to the line from the hinge to where the force is applied. And so the distance for this 20 Newton force is this. And that's just the radius of the disk, which is 0.3 meters. So we have a force of 20, a distance of 0.3. with the hinge at the center, a force here in this direction will make it rotate clockwise. So we're going to take the negative. And this gives us negative 6.0 Newton meters. And so the net moment, the net torque, is the sum of these three things. And so that's equal to negative 6 Newton meters. And now we have everything we need to put this into rotational Newton's second law. The net torque is equal to the moment of inertia times the angular acceleration. And so the angular acceleration is negative 266.6 repeating, and that's in radians per second squared. Okay, so now we figured out the angular acceleration. Now what we need to do is figure out, do the circular motion calculation for that point A. Okay, so we know that the angular velocity, that was given that it's counterclockwise at 10 radians per second. We calculated that the angular acceleration is clockwise, so it's this direction. So at this point that we're asked about, the velocity vector is this way. The angular acceleration vector is the opposite way. The angular acceleration vector is, the angular acceleration is the way that I drew it here. What I drew here in the green vector is the tangential acceleration. And then the centripetal acceleration is towards the center. And we have all the values that we need to calculate these. So let's just start going through them. All we're looking for is the total acceleration. There's no need to calculate that velocity vector. It wasn't asked for. So I'll just go right into that. The centripetal acceleration magnitude is omega squared times r. So that's 10 squared times 0.3. So that is 30 meters per second squared. And that's in the negative I direction. So negative 30 meters per second squared times I. And now we'll go to the tangential acceleration. The magnitude is the absolute value of alpha times r. So that's 266.6 repeating times 0.3, and that is 80 meters per second squared. You can see from the drawing we figured out that the tangential acceleration is in the negative j direction. So that's negative 80 meters per second squared times j. Now the total acceleration is the sum of those two parts. So the total acceleration of that point A is negative 30 meters per second squared times I minus 80 meters per second squared times j. Let's do one with a rectangular beam. So let's say for the second example, we have a rectangular beam like this. Let's say the length is 1 meter. And let's say in this case, we're not even given a thickness. So we're just going to assume that this thickness is small compared to the length. And we're just going to treat it like 0. It turns out that that gives you a pretty good approximation a lot of the time because of the fact that you're squaring these dimensions in the formulas. And we'll say that the mass of this beam is 5 kilograms. And at this instant, let's say that this beam is moving, let's say it's sort of falling down, which would mean that the angular velocity, it's counterclockwise, so this is going to be positive. So let's make this 4 radians per second. And we want to calculate the acceleration of this point A at the end. And we're going to assume, well, I guess we did in this one too. I'm going to assume that the downward direction is toward the bottom of the page, so we're going to have to put gravity in this problem. Okay, so the first thing we're going to do, again, is use rotational Newton's second law to calculate the angular acceleration. And so I'll start with a free body diagram. Over here, we have our 2 unknown forces. Those are applied to the beam by the hinge. And then in the middle, we have the weight force, and that is 5 kilograms times 9.8, so 49.0. Now we have to calculate the moment of inertia for this rectangle. This is equal to 1/3 times 5 times the length squared plus 1/12 times 5 times 0 squared. So you can see this term just goes away. And we're left with 1.6 repeating kilogram meters squared. And now we have to calculate the moments applied to this body by the forces. So the moment or the torque applied by those forces R is 0, like it always is. The moment applied by this 49 Newton force, I guess I'll call it mg, is plus or minus 49 times the distance from the hinge to where the force is applied. We didn't have to move the force at all along its line of action in this case because that force is already perpendicular to that red line. The length of that red line, d, is half of the length of the beam, so just 0.5. And now you have to think this force with the hinge over here at the right, would this weight force make this body rotate clockwise or counterclockwise around that hinge? This force would make it rotate counterclockwise, so we want the positive. And so the moment produced by the weight force is 24 24.5. And this is Newton meters. Add these up and you get that the net torque is 0 plus 24.5, so just 24.5. Now we can put these into rotational Newton's second law. Which says 24.50 is equal to 1.6 repeating times alpha. So alpha is equal to 14.70, and this is radians per second squared. Now that we have the angular acceleration, all we have to do is the circular motion part. So if this is the beam and the rotation is about this point here, then the circle of the path is going to look like that. Okay. The angular velocity and angular acceleration are both counterclockwise in this case. So omega and alpha are both this way. And that means that the velocity is this. And the tangential acceleration is in the same direction. And then the centripetal acceleration is always towards the center. And now we just have to calculate the two parts of that acceleration. The magnitude of the centripetal acceleration is omega squared times r. Omega was 4. So this is 4 squared times the radius of this circle is the length of this beam, so 1. And we get a centripetal acceleration magnitude of 16 meters per second squared. That's in the positive I direction. And so this is 16 meters per second squared I. And then the tangential acceleration magnitude is the absolute value of the angular acceleration times r. So that is the 14.70 that we just calculated, times the radius of this circular path, 1. And so this is 14.70 meters per second squared. It's in the negative j direction. And so we get negative 14.70 meters per second squared j. Add those two parts together, and the total acceleration is 16 meters per second squared I minus 14.70 meters per second squared j. I want to walk you through one more type of problem, and this is where we use rotational Newton's second law, but we also are using Newton's second law with the acceleration of the center of mass to calculate. Usually you would use it to calculate the contact force being applied to the body by the pin. And the key to this is that when you use Newton's second law with a rigid body, the acceleration that you're using in the equation is the acceleration of the center of mass. So Newton's second law with a rigid body looks like this. The net force is equal to the mass of the body times the acceleration of the body's center of mass. Okay, so let's see how this works in a rigid body problem. Let's say we have a beam in this orientation. And let's say the length of this beam is 0.5 meters. I'm going to assume that the thickness is small compared to the length, and so I'm just going to ignore it. I'm going to treat it as 0. Like I mentioned before, that can give good results sometimes. The mass of this beam is, I'm going to call it 1 kilogram. And I'm going to say that there's a force applied this way of 10 newtons, a force applied this way of 10 newtons. And we want to calculate first the angular acceleration. Second, we want to calculate the acceleration of the center of that body. And then the last thing we're going to do is we're going to use our calculation for the acceleration of the center of mass, the center of this body, in Newton's second law to calculate the force applied to the beam by the pin. And I'm going to say that instead of this being at rest when these forces are applied, we're given that the angular velocity of this body is 5 meters per second. Since it's positive, that's counterclockwise, so it's moving in a counterclockwise circle. And what we're going to see in this example is that those forces Rx and Ry that we put in all these problems and they produce 0 moment. Yeah, they produce 0 moment because they're happening at the pin, but they still are forces. And we can still use Newton's second law to calculate what those forces are. Okay, so the first thing I'm going to do is calculate the moment of inertia. So I for this body, we're at the end of the length, so this is going to be 1/3 times the mass times the length squared, plus the other term is going to go away because we're assuming the thickness is 0. And so we get a moment of inertia of 0.08, and then 3's repeating, and this is kilogram meters squared. And now I'll draw the free body diagram. And this is the free body diagram I'm going to use for the rotational Newton's second law and the one that I'm going to use for Newton's second law later when we're calculating those contact forces. So at the pin, we have our unknown forces, Rx and Ry. Then at the center, we have the weight. That's 1 times 9.8, so 9.8 newtons down. And then we have the 10 newtons going this way. and the 10 newtons going this way. Well, the moment produced by R, as always, is 0. The moment produced by the weight, in this case, you can see if you extend the line of action of the weight, it goes through the pin, so that's also going to produce 0 moment. Then the moment produced by the 10 at the center, I'll call that moment at C, okay? That is plus or minus a force of 10 and a distance of half of the length of the beam. You can see that that would make this rotate clockwise, so we're going to take the negative, so that's negative 2.5 Newton meters. And then the moment, I'll call it at the end. Wow, the lawn out stuff outside is loud. Okay, but plus or minus 10. This one, the distance from that perpendicular force to the pin is the full 0.5. That's going to make it rotate counterclockwise. So this is positive 5.0. Now I'll put this into the moment equation, the rotational Newton's second law. And it says negative 2.5 plus 5.0 is equal to 0.083 repeating times alpha. And we get that alpha then is equal to positive 30 radians per second squared. Okay, so now we've calculated the angular acceleration. That's part A. Now we want to calculate the acceleration of the center of this body. And even if I didn't ask for that, we would need that in order to calculate the forces applied by the pin. So now we're going to a circular motion problem. So for part... Okay, so here is, we're doing a circular motion thing now. This is the beam. And we're analyzing the motion of the center of the beam. We know that the angular velocity is this way. The angular acceleration is also this way. So we know that the velocity of this point is going to be like this. The tangential acceleration is also going to be in that direction because the angular acceleration is also counterclockwise. So there's the tangential acceleration. The centripetal is towards the center. And now we need to figure out the magnitudes of those two. The magnitude of the centripetal acceleration is omega squared times r. We were given that angular, the angular velocity times r, I'm sorry. We're given that that's 5. And so this is going to be 5 squared times the radius of this circular path. That's not the whole length of this thing. It's only half of the length because we're at the center. So this is times 0.25. And so we get a magnitude of the centripetal acceleration of 6.25 meters per second squared. We can see that's in the positive j direction. So the centripetal acceleration vector is 6.25 meters per second squared in the positive j. Now do the same thing with the tangential acceleration. The magnitude is the absolute value of the angular acceleration we calculated times that same r. So that's 7.5 meters per second squared. You can see that that's in the positive I direction. So this is 7.5 meters per second squared I. And that means that the total acceleration is just the sum of those parts, which is 6.25 meters per second squared I plus 7.5 meters per second squared J. And now we can use that with regular Newton's second law to calculate the force applied to this body by the pin. What we're calculating here are these two components of the force. Where's my free body diagram? Rx and Ry. And this one should say X. The one that's in the I direction should say X. I'm going to use the same free body diagram here. And so we're going to add up these forces. Anything that's in the I direction, we're going to have separate in the I part, and anything in the Y direction or negative Y direction, we're going to have separately in the Y part. So Newton's second law says for the X forces, we have Rx. Then we have 10 in the negative I direction. And then we have 10 in the positive I direction. So these are the forces in the I direction. You can see you have to use the signs in there, the directions. And then for the Y forces, we have Ry minus 9.8. And these are the forces in the J direction. And these are equal to the mass of the body, 1 kilogram, times the acceleration in the I direction, plus the mass times the acceleration in the J direction. Okay? These are the acceleration components of the center of mass. That's what you have to use in Newton's second law. And so now we have two equations. The first one is the I equation. So what that says is we take all the stuff in the I direction, and it says Rx minus 10 plus 10 is equal to 6.25. The 10s cancel each other, and so we get that Rx is equal to 6.25 newtons. Now we'll go to the J equation, and that says Ry minus 9.8 is equal to 7.5, and so Ry is equal to 17.3 newtons. Now, if you've taken the signs into account like you should, what you get are the directions of these components. We got positive for both of these. They could come out positive or negative. If it comes out positive, it's in the positive I or J direction. If it comes out negative, it's in the negative I or J direction. And so our final answer for this force that's applied to the body by the pin is equal to 6.25 newtons, in this case in the positive I direction, plus 17.3 newtons, in this case in the positive J direction.